In this video, we're going to take a look at friction and revisit some concepts that we learned in AP Physics 1 and extend them just a little bit. So friction is essential in our everyday life. We use friction to pick things up. When we grab something and pick it up, static friction is helping us to do that. Just walking or biking or driving anywhere, we use friction to change our direction and to keep us on the road or the path. When we write with a pencil or even a pen, we're using the friction to transfer that ink or graphite onto the paper. And anytime we build something with nails or screws, that's friction that's holding it together, or weaving a cloth or anything like that. Friction is very important. In fact, we depend on it for our everyday life. However, we do want to try to overcome friction at times to make things more efficient. All right, 20% of gasoline used in an automobile goes to counteract friction in the drivetrain. So friction is imperative, it's needed, but it can also be a disadvantage in stealing some energy. So we try to make things more efficient to keep things in motion by reducing that negative friction while keeping the positive friction that's needed. So think about these three experiments here, and you can even do them or just think of them conceptually. If you slide a book across a counter, the book slows and stops. If you push it so it's sliding, it'll eventually come to a stop. So there must be an acceleration parallel to the surface and opposite the direction of motion. And if you push a book at a constant speed across the counter, there must also be an equal and opposite force opposing you, because you're pushing, exerting a force, so that should cause it to accelerate. However, if you're pushing at a constant speed, then there's got to be some force opposing it. And also think about pushing a crate that's very heavy and does not move. And so to keep the crate stationary, there has to be an equal force that's pushing back on you, opposing your pushing force. However, if you push hard enough, then that opposing force must also increase to keep the crate stationary. However, there's a limit to which if you push hard enough, it will then start to move. So this kind of gives us an idea of how friction works and the two different types of friction. And there are two types of friction. There's static friction and there's kinetic friction. And the key here are all in these adjectives. Static friction happens when the surfaces are static. Now that doesn't mean the object is static, but it does mean that the surface is static. And the opposing force that prevents an object from moving is what we call the static friction. And so we want to think, can we have a magnitude from 0 to some maximum here? And so we have this static frictional force that can start at nothing if we don't have an opposing force, but it can get up to some threshold, and we'll talk about the formula for that in a moment. However, once the maximum is reached, once we get to that maximum, forces are no longer in equilibrium. The object starts to slide, and that's when we get to kinetic friction. So when the surfaces are moving with respect to one another, then we have kinetic friction. All right, and this always opposes the direction of motion. Now, static friction also opposes the direction of motion, but it's not quite as intuitive. It opposes the intended motion. Static friction opposes the intended motion, the motion that the object would move if friction were not there. And kinetic friction is just in the opposite direction of the object's motion. And this only has one value, not on a continuum like static friction is, just one value, no threshold that we can calculate. All right. And generally, most surfaces, the kinetic friction is going to be less than the maximum static frictional force. So let's consider this object here where the frictional force is 0 in part A. And then we exert some force here, F, and yet we still don't move it. There's no motion. Okay, and so with that no motion, then there has to be some frictional force opposing it, and that frictional force is equal to the force we exert. Well, we push a little harder, and still there's no motion, so the frictional force has to equal that even bigger force. And then we push a little harder, still no motion, so the frictional force is increasing with that force applied because there's no motion. However, once we get high enough to overwhelm the static friction, then we start to accelerate in that direction of the applied force, and kinetic friction comes in. Kinetic friction does not change. All right, kinetic friction is the same, and typically it's weaker than static friction, so that's why we get this acceleration. Now, if we decrease our force such that we're moving at a constant velocity, then we have the force applied is equal to the kinetic friction. All right, this graph right here in part G is actually a nice depiction of what happens to frictional force. So before the object moves, before this breakaway point, the friction increases here, and it's almost linear. All right, it's almost a linear relationship. And then there's this breakaway where we drop, and then we're pretty much constant with our, and we'll just, for our purposes, we'll assume it's constant because the variation is so slight. And so the kinetic friction is constant after the breakaway point. Now, why do we have friction? Well, on a microscopic scale, the surfaces are bumpy, okay? Now, if we want to go even smaller, if we want to go on an atomic scale, really the reason we have friction is an interaction between the valence electrons. Okay, now we're not going to get into that so much, but we just need to know that, all right, on the small scale, all surfaces are bumpy and have some texture. Even if they might feel smooth to our touch, they do have some texture. And friction occurs when we have these contact points and the contact points slide. Now, there is such a thing called cold welding that happens if you have two pieces of metal that have too many contact points, and when they try to slide, they can't, and they actually fuse together. Now, this actually happened and was an issue in the International Space Station. We had some just basically like raw metal on the ship and the space station. When they came and hit, they fused together because they were so like each other, and the surfaces had so many points of contact that they wouldn't separate. And so it was like someone heated them up and welded them together. So this is something that does happen in industry that you have to be aware of, and keep that in mind. Another thing to keep in mind here when dealing with friction, the normal force comes into play. So the greater the normal force to the contact plane, the greater the force of friction is going to be. And so we'll see that in the equation in just a second here. But increase in normal force is going to increase the friction. And sliding that is jerky due to the ridges on the surface typically produces some type of squeaking, squealing, or some sort of sound, which once again is another way that we lose energy. Now, we're just talking about forces here. We'll get into energy later, but still, to keep that in mind, that's one of those negative effects of friction. So how do we calculate friction? Well, we have this equation that when we're dealing with static friction, the maximum, now keep in mind, this is the maximum static friction, is equal to mu times the normal force. Well, what is mu? Mu is the coefficient of static friction. Now, this is predicated by the surfaces in contact. This can only be found empirically. We can't find this theoretically. So typically we look it up in tables or we do experiments to find these coefficients based on surfaces. Kinetic friction is very similar, except there is no max here. It's just equal to one value, and so it's mu times Fn once again. But then what this mu here is the coefficient of kinetic friction, which is going to be a little different than the coefficient of static friction. Typically it's a little less. Now, both coefficients are usually between 0 and 1. If you have a coefficient of friction that is equal to 1, that's pretty sticky. Now, if you get one greater than 1, we could consider some adhesives to have a coefficient of friction greater than 1. But typically everything's going to be between 0 and 1. So what I want you to do is pause the video here, read this checkpoint, and try to answer those questions. The answers are given to you down here at the bottom. But just give this one a shot to kind of think through how friction is involved. One last thing to consider here with friction is if we have a force applied at an angle, how does that affect the friction? Well, keep in mind the normal force is what determines the magnitude of our friction, that and the coefficient. And so if we exert a force at an angle downward on an object, that's going to increase the normal force because there's a component of that force that opposes the normal force. And so that is going to cause a greater normal force, which will then cause a greater threshold in static friction, or if this object is moving, a greater value of the kinetic friction.